bullet-dwarf collision scenario?
Hi, can you hear me? Yeah, hello. My name is Yimeng Tang, and I'm a rising third-year graduate student here in Santa Cruz. And so the topic I will talk about today is to testing the bullet-dwarf collision scenario in the NGC1052 group. So Engine Shen had a great talk in the morning, so I will talk about this just in observation and our latest results. So in the past decades, we have established a great image like there's a great connection between the galaxy and the dark matter halo. So dark matter galaxy is very interesting because they should have a larger fraction of dark matter. But in recent years, people have started to find some exceptions. The first one is NGC1052 DF2, and the second one is DF4. Just shortly after that, in the same galaxy group, these two galaxies are ultra-diffuse galaxies, and they have similar effective radius, similar stellar mass, and people use HiPACC to measure their stellar velocities and get a very low sigma. So it means the whole dynamic mass just comparable to their stellar mass, which means they almost have no dark matter. And also DF2 and DF4 have very unusual global cluster systems that are too luminous, too extended, and too flattened. So it's just very similar to the brightest global clusters as we see in the Milky Way. It's very unusual for global cluster, for the dwarf galaxies. And also, those global clusters have very similar HST colors, which means they have very similar ages, about 8 gigayear and minus 1.3 in metallicity. It just means maybe they have a single formation burst. So why do we care this? Because both of the no dark matter nature and the unusual global clusters is not very common in the dwarf galaxies, but DF2 and DF4, they have both. Usually people explain the no dark matter nature of the dwarf galaxies from the tidal stripping. I'm showing you some plots from Moreno 2022 with Fire2 simulation. And so the physical picture is when a dwarf galaxy falls into a massive halo, it gets disrupted, and dark matter will be stripped first, and then the stars. So you get a no dark matter galaxy. So in this scenario, tidal stripping typically produces strong tidal features, as you see here. It should be observable. But this theory does not explain the unusual global clusters in those two galaxies. So here's another scenario. Just people come up with to explain the global cluster is the extreme stellar feedback. So the picture is those galaxies, they formed in early collapse times, and the gas density was very high, and you will have very high star formation rate and many global clusters, which brings extremely strong feedback. And it expands the size of the galaxies a lot, and also push the dark matter all the way to the larger radii. So those galaxies in this scenario is not real dark matter free. They just have a very different dark matter radial profile. So when you measure the dark matter, just like with commonly used density profiles, you get a wrong answer. You underestimate the dark matter halo mass. But in this scenario, you are still considering galaxies evolve independently. But is it just a coincidence that we see DF2 and DF4? They share those very many similar properties and in the same group. Why we didn't see the same thing in other galaxy groups? So recently, people come up with another idea. It's just bullet-dwarf scenario. So Shane had a talk in the morning, so I will not dive into this theory details. But to be brief, it's just you have two gas-rich dwarf galaxies, and they have a head-on collision. And this collision produces a separation between the gas and dark matter halo. And you will have a trail of gas clumps in between, and each clump can collapse to form a galaxy. So the natural question here is just, if this is a real thing happened, should we expect more galaxies in this collision, not just DF2 and DF4? So maybe we want to find more clues in the sky. So let's see what happened here. So yes, we have about 10 galaxies on the same linear structure here. And so DF2 is here and DF4 is there. So here is some key questions we want to answer. So do these galaxies along the trail share similar properties to DF2 and DF4? Like, do they also have no dark matter, or they have unusual Google cluster systems? And do these trail dwarfs have physical connections? So do they form independently, or they just form in the same event, just in the bullet-dwarf collision? So I would like to show some latest results from our observation. So to answer these questions, we investigate the dwarf galaxies along the trail with new HST observation and also some ground-based data from U-band and mid-infrared in space. We use GalFit to do the photometry and measure their morphologies. And we use Prospector to run SE fitting to get their cell populations. We also have CAC spectrum to measure the radial velocity. And our sample consists of 10 trail galaxies, because 2 of them are just too fan, and we cannot do that. And other dwarf galaxies in the same group to provide some further comparison. Here's an example of SE fitting of DF2. So let's see, this is very interesting plot about position angle. So RA on the x-axis and DEC on the y-axis. The orientation of each line segment means the position angles. So you see, the position angles of trail galaxies show nice alignment along the trail. And so the trail itself not have to be perfectly a straight line. You can be look like a snake. But for the non-trail galaxies, the blue points, they just like random. So this pair alignment of the trail dwarfs parallel to the trail structure itself strongly stress physical connection among the trail dwarfs. So some more interesting thing happened to the radial velocities. So we get the spectrum of 7 of them, the trail galaxy, and we have 2 more data points to come. And so you can see also the radial velocity on the y-axis show a great correlation with their position along the trail on the x-axis. So you just see a great radial velocities alignment. So this, again, suggests that you really have a linear structure in the 3D place. It's not just like a 2-dimensional projection onto the sky from a random distribution. So one question is, can we really predict that from the simulation or theory? Let's try. So about position angle, we don't really have a clear image from the theory. We just have some quantitative speculations. So the thing is, when you have a collision, after the collision, you have a trail of gas clumps here, and they are stretched along this direction because of the collision. So when the gas clumps form new galaxies, you expect, because they are stretched, you expect more stars formed on the direction that's parallel to the trail, and fewer stars perpendicular to the trail. So you expect a position angle like this. They're just like bullet shape galaxy. Yeah, and the radial velocity is much easier to understand because newly formed galaxies, they originate from the same location here, and their orbits should be just nearly on the same plane. So it is expected that they have a great arrangement on the radial velocities. So one thing to mention here is, just you see some numbers here. If we're tracing back in time, just based on the difference of line of sight distance and the relative radial velocities of DF2 and DF4, we get like age of 6 gigayear. Maybe it's just the time when the collision happened. So let's see what's going on about the stellar populations. So as we said, we use prospector to get the stellar populations. So let's see the mathematical relation first. So you see the trail dwarfs, the red points, they're roughly on the same relation. And it agrees well with Simon 19 relation for the ultra-diffuse galaxies. But the off-trail dwarfs, the blue points, they really have a very different distribution. So that could mean like they have like very different formation and evolution history. And also here, you see the age on the x-axis. And so trail dwarfs roughly have the same age. But I mean, the alpha is large, but we cannot reject that they have the same age. And the off-trail dwarfs are also very different. And the difference is mainly come from the stellar age. The trail dwarfs is in average 2.5 gigayear older than the off-trail dwarfs. So let's just overview what we did. Just do some bridge between the observation and theory. So we checked the position angles. We see a great alignment. So it agrees well with bullet-dwarf scenario. But for the other two theory, the tidal stripping and extreme feedback, those galaxies are expected to evolve independently. So there's no reason to expect position angle alignment. Also, same thing for velocity. And for the stellar population, we cannot rule out anything here, but since the trail dwarfs looks like systematically older than the other dwarfs in the same group, so give some support to the bullet dwarf scenario. And so with our data, we cannot really directly measure the dark matter content because it's so hard, especially for those low mass galaxies. Maybe the velocity dispersion is smaller than 5 kilometers per second. But what we can do with our data is to measure the line of sight distance to get some idea of global clusters. And also we can make use of the deep imaging from Dragonfly to get some idea about tidal features. But last but not least, very important to mention here is we really need support from the theory end, because we really don't know too much about the theoretical predictions of the bullet dwarf. So this is a summary slides. I will stop here and take questions. Thank you.
Any questions?
So is there something that sets a mass scale at the place where these sorts of collisions can cause new things that look like galaxies to form? So like in a bullet cluster style collision, the gas is all too hot and you don't form things in that collision region. But then at the dwarf scale, it seems like you do. So where does the transition between those two things happen? Do you have any idea?
I don't know.
Okay.
Yeah.
It was worth a shot.
Yeah, I mean, like, should have some predictions from the simulations. Yeah.
Any other questions?
Thanks. It's probably a very stupid question, but in your projected position versus radial velocity plot. Why were the uncertainty on the position so uncertain? I mean, it's like greater than 5 arc minutes. Why is that?
Yeah, the thing is, let's see, it's hard to really define a trail, right?
Oh, okay.
Yeah.
I see what you mean. Okay.
Yeah.
So please, the next speaker, come up and set things up. And in the meantime, okay.
A simple one. What causes the variety of these intermediate dwarfs? There seems to be a large variety in terms of shapes and sizes and things like that. Is that naturally from the simulations as well, or are those size distributions unusual?
You mean these galaxies? Yeah, I mean, I don't know the real answer, but I mean, it could be have some, interaction with some other system afterwards, after the collision. Yeah.
Okay, so you said that 2 more data points are coming in your radial velocity plot.
Right,
So
right.
when do you expect it to come?
I don't know, maybe even 4.
Okay, let's thank the speaker one more time.